Welcome to the Explainer. Today, we're unpacking a fundamental flaw in how machines learn and the completely ingenious mathematical balancing act data scientists use to actually fix it. We're going to look closely at a concept that is literally at the very heart of modern machine learning. It's the thing that dictates whether an algorithm is going to succeed brilliantly or just fail spectacularly when it's actually deployed. I mean, think about it. Why does a model that looks absolutely perfect in the lab completely break in the real world? Let's get into it. Okay, imagine a student who perfectly memorizes a practice test, but then, completely bombs the final exam. When they sit down for the real thing, any slight variation in a question just completely throws them off. Why? Well, because they didn't actually learn the underlying concepts, right? They just memorized the specific examples. Now, in machine learning, we see this exact same phenomenon. And honestly, understanding why it happens is the absolute key to building models we can actually trust.
To solve this mystery, here's our roadmap for today's explainer. We'll start with the basic machine learning goal, look at the trap of empirical risk, break down the bias-variance tradeoff, and then introduce the hero of our story, structural risk minimization, before seeing how it all gets put into practice.
Section 1. The machine learning goal. Let's start by looking at the default rulebook machines use to learn from data. The standard approach in the field is called Empirical Risk Minimization, or ERM for short. ERM is basically a learning paradigm that grades the computer solely on how well it answers the exact questions it was given during training. The algorithm just looks at the data you provided, the empirical sample as we call it, and finds a mathematical rule making the fewest mistakes on that specific data, which makes intuitive sense, right? If you want a computer to learn, you grade it on how well it masters the material you hand it. You just find the rule with the lowest empirical risk. Moving to Section 2, the trap of empirical risk. Because here's exactly where things start to go wrong. What happens when a model is so focused on acing that specific practice test that it completely misses the bigger picture? Consider a model that is simply not complex enough. Think of a basic degree 2 polynomial trying to fit a really complex set of data points. We call this underfitting, or operating with high bias. The model's internal rulebook is just way too rigid. It's kind of like trying to draw a highly detailed portrait using only a giant thick marker. Sure, it captures a very basic curve, but it completely misses the actual shape of the data. And that results in a high error rate, even on its own training set. But watch what happens if we bump up the complexity just a little bit, say to a degree 3 polynomial. Boom, we get a just right fit. Notice how this curve naturally follows the underlying trend of the dots without being totally obsessed with hitting every single one perfectly? This model hasn't memorized the data. It's actually learned the pattern. So when new, unseen data comes in, this curve is perfectly positioned to make accurate predictions. However, if we let empirical risk minimization run completely wild, giving the algorithm a highly complex degree 10 polynomial to work with, well, you can see it twists, turns, and literally contorts itself to perfectly pass through almost every single dot. It has perfectly memorized the training data, hitting a near-zero empirical risk. But, and this is a huge but, it's also memorized all the random noise, all those little errors and fluctuations in the data. This trap is known as overfitting. If you drop a new, unseen data point into this chaotic chart, the model's prediction won't just be a little wrong, it'll be wildly inaccurate. Which brings us to Section 3, the bias-variance tradeoff. This visual proof leads us right to a mathematical crossroads in statistical learning theory.
So the absolutely crucial point here is the trade-off between two types of errors. On the one hand, we have approximation error. This is the underfitting we just saw with our rigid degree 2 polynomial. But if you try to push that error down by giving the model massive flexibility, like our chaotic degree 10 polynomial on the right side there, your estimation error completely shoots up. The model becomes way too sensitive to the specific finite sample of data it was trained on, which causes it to overfit. You basically can't minimize one without inflating the other. It's a real catch-22.
Let's look at Section 4, Structural Risk Minimization, or SRM. So how do we actually fix this mathematically and ensure our model is just right? Enter structural risk minimization. Formulated by the pioneer of statistical learning, Vladimir Vopnik, SRM is basically a brilliant extension of ERM. See, instead of just asking, hey, how accurate is this model on the training data, SRM also asks, wait, how complicated is this model? It explicitly balances the empirical risk with a mathematical penalty for the size or the flexibility of the function space being used. In everyday terms,
It penalizes the model for having too many mathematical options to choose from. So in practice, SRM works in this really elegant, structured three-step process. First, it organizes models into nested classes based on their complexity. Just think of this as grouping our polynomials from degree 2 to 3 all the way up to 10. Second, it mathematically penalizes the highly complex ones, essentially taxing them for being too flexible. And third, it selects the model that minimizes the combined total of the training error plus that complexity penalty, the whole shebang. What SRM is actually doing here is relying on a bound minimization approach. Since we can never, ever directly measure the true risk, how the model will perform on all future data in the real world, we rely on this bound. We just accept that the true risk is going to be less than or equal to our empirical risk, plus a bound on the estimation error. And that bound, it grows as the model's complexity increases. By minimizing this entire right side of the equation, SRM pretty much guarantees that the gap between practice performance and real-world performance stays tightly controlled. Moving to our final section, Section 5, putting SRM into practice. We have this beautiful mathematical theory, but why does it matter for real-world applications? Well, in practice, SRM is the safeguard that makes machine learning actually reliable. In high-stakes fields, like financial machine learning, for instance, where data is incredibly noisy and high-dimensional, you absolutely cannot afford an algorithm that just memorizes random market fluctuations. So engineers apply SRM principles through something called regularization. By adding a mathematical stabilizer, like a built-in penalty, directly into the algorithm, it forces the AI to prefer simpler, more robust rules over chaotic ones. It ensures the model isn't just chasing random noise. This quote from the source material actually hits the nail on the head and perfectly sums up what you should take away today. A model's flexibility is a double-edged sword. In learning theory, we often measure this with something called the VC dimension, which is essentially a mathematical rating of how flexible and capable a model is at perfectly separating data points. Now, to lower your initial bias, you need a wider set of functions. But as that VC dimension increases, so does the dangerous gap between your training error and your real-world test error. The true brilliance of structural risk minimization is that it refuses to look at accuracy in a vacuum. It absolutely forces the model to justify its complexity. I'm going to leave you with this final thought to ponder. Today, we are training algorithms with billions, literally trillions of parameters. We're talking massive oceans of complexity. As these models continue to grow in size and power, applying the fundamental principles of structural risk minimization, forcing an algorithm to find the simplest possible path to the truth, is going to be more important than ever. Thanks so much for joining me for this explainer, and keep questioning the complexity behind the AI you interact with every single day.